This week you're looking at standing waves on a wire. So what should you hope to learn this week? You'll be hopefully understanding the relationship between linear density, tension, and wavelength, and in doing that, experimentally obtain the linear density of a particular material. So how you'll be doing this? Well, part one in the lab, you'll just be measuring standing waves on a wire and learning how to do this properly with your correct uncertainties. And in part two, you'll be using similar measurements to determine the linear density of that wire from wavelength versus tension measurements. So how exactly does that work? So the equation down here, mu naught equals Ft over V squared, that's the equation for the linear density of a wire, where mu naught is the linear density, Ft is the tension force in the wire, and V is the wave speed. So the wave speed is just equal to F times lambda, the frequency times the wavelength. And so if you substitute that into the first equation, then you get an equation that gives you the relationship between wavelength squared and the tension force, where you've also got frequency and your linear density. But if we're using a constant frequency source, like our power source, which is run at 50 Hertz, then we take a bunch of different wavelength measurements for different tensions in the wire. Then our only unknown is linear density, and we can figure that out from slope when plotting our data in a graph. So I'll bring you over to the lab now to show you what you need to do. So this first part of the experiment, you're looking at just measuring standing waves. So this is all the equipment that you need here for the first part of the experiment. This is your mass carrier. These are the weights that go on top of the carrier when you get up to it. This here is just a block for connecting a current to this side of the wire. And here are your power supplies. You could get either of these, just make sure that you're on 12 volts, and if you're on this one, that you're getting the AC power supply rather than the DC power supply. Okay, so once you've got your circuit set up and you're ready to start getting your loops, start with your block at this end with the block towards the light source, and just slowly move it back. So you'll eventually start to see the wire vibrate, which means you're close, and so you just need to keep slowly tweaking it until you increase that amplitude. So I've put the black paper here just so you can see the loop better, but you'll notice it's quite a big amplitude there, so that's good for your first loop. Okay, so once you've adjusted, your first loop should look something like this. I've just put the black paper down so you can see the loop better. In the lab you won't have that. Okay, so you also need to get an error on where the wavelength is. So to do that, you want to adjust this both forward and back just to reduce the amplitude of this wave. So in your manual it says to 25% amplitude. That's kind of ambiguous, but just make sure you can still see some sort of loop so you know that there's still some margin of error where your wave can be. So this is bringing it closer, and again you come to the maximum one and then bring it back out a bit further, and where you can just sort of see it vibrating, and that will be your larger length error. Okay, once you're done with the first loop, you'll move the block about twice the distance out until you find two loops, and so this is what it will look like. Okay, once you're done with the second loop, similarly you go ahead and aim to get 3 loops, and making sure you're taking your 25% loops for both of them along the way, so you've got all your errors. Okay, so for the second part of the experiment, you're wanting to see the relationship between wavelength and tension that you're putting on the wire, and you're using that to determine the wire's linear density. So you'll be doing the same thing, measuring the wavelengths, but you want to be adding weight onto the carrier each time. So just keep repeating the experiment, adding new weights. For the first part of the experiment, you need to have just your mass carrier plus 1 additional weight. So it's just like this, and don't forget in your calculations that you need to take into account the mass of the carrier, which is the same as one of these, which is just 50 grams. Okay, so once you've got your mass carrier set up, you just put the wire over the pulley here, and now you're ready to turn on your circuit if everything else is set up. But be sure to check with your demonstrator. Okay, so now just a few useful hints for this lab. One of the problems that students have is with the ambiguity of your 25% amplitude loop when measuring your uncertainties for wavelength. Now, it doesn't have to be exactly 25%. This value is a little bit ambiguous, so as long as you're nearby, or at least you've still got a vibrating wire for the loop, it doesn't really matter. We just want to get some sort of idea of where the uncertainty for the wavelength lies. Secondly, don't forget to take into account the mass of your carrier when measuring the weight for your tension force. So the mass of the carrier weighs just the same amount as one of the weights that you put on, so it will make a difference if you leave this out. And lastly, with units, some people are still a little confused around this, so I'll explain how it works for linear density. So you can get this from your equation. Your linear density is equal to force over velocity squared. So the units for that is just newtons, so kilogram meters per second squared, divided by units of velocity, which is meters per second, all squared. And then so you can see this equation and cancel out one of the m's on the top and get rid of your second squared, and it becomes just kilograms per meter, which is a mass per unit length, which is what we expect for a linear density.